So we're going to look at some calculations involving moles and particles. So as you might already know, 1 mole is equal to Avogadro's number, which is 6.02 times 10 to the power of 23. And this relationship can be used to measure anything, right? If you have 6.02 times 10 to the power of 23 donuts, you would call that 1 mole of donuts. Now, that works. We're not really going to be looking at situations like that, but it is a relationship that makes sense. Another way of thinking about it, it's very similar to if we say 1 dozen. So if I say 1 dozen, let's keep going with donuts. So if I'm looking at 1 dozen donuts, you know you're talking about 12 donuts, right? And I want you to keep this in mind. If I'm referring to 1 mole of something, I'm counting how many of that thing there is, there would be 6.02 times 10 to the power of 23 donuts. Or if you know that if you're looking at 1 pair, right, you're looking at 2 socks. So keep this in mind as we're going through these calculations. It'll help you make sense of what conversion factors we are looking at. Now, in this case, or in the case of this module, whenever we're talking about 1 mole, you will always see not the unit of donuts, but rather particles. Right? Because we're talking about chemistry, we're talking about atoms, we're talking about molecules, we're talking about particles. So I know we're talking about particles, but we are rarely going to see the unit of particles. And that's because you can write these particles in 3 different ways. So depending on the type of compound or element that you are given, you would use, instead of particles, you would call them by a special name. So if you have an ionic compound, and I'm sure you know how to identify an ionic compound. It's made up of a metal and a nonmetal. If you've got an ionic compound, you would call this 6.02 times 10 to the power of 23 formula units. Right? And that's only if you've got an ionic compound in your question or the situation that you are looking at. If you've got a molecular compound, you would call it molecules. So 1 moles of a molecular compound would be equal to 6.02 times 10 to the power of 23 molecules. And lastly, if you're looking at an element that is by itself, right, for example, any metal, you would call it 6.02 times 10 to the power of 23 atoms. Right? So I know we're talking about particles, but depending on the situation, instead of saying particles, you would say formula units, you would say molecules, or you might say atoms. And we'll look at different situations where you might have to use one of these. So if you remember from the first module, when we did math skills, we learned about dimensional analysis. And an important factor of dimensional analysis was being able to determine how to represent a conversion factor. So this is an example of a conversion factor. 1 mole is equal to 6.02 times 10 to the power of 23 particles. Depending on what you are given in the question, you might represent this in 2 different ways. So for example, you would start off by you could write 1 mole over 6.02 times 10 to the power of 23 particles. Most of the time when you're doing calculations, you probably wouldn't say particles, you might say formula units, molecules, or atoms, but for now, let's just use particles. So you might write 1 mole over 6.02 times 10 to the power of 23 particles, or what you might do is write 6.02 times 10 to the power of 23 particles over 1 mole. Now, why might you choose this one over this one? Whatever unit you want to cancel out, you would have to write this at the bottom. And when we do our practice problems, you will see examples of us doing this so that we can cancel units out. So let's put this into practice. If I'm talking about 1 mole of Fe, So remember, this is an element that it's by itself. I am looking at 6.02 times 10 to the power of 23 atoms. Remember, so this is the context in which you'd use atoms, when there's an element that is by itself. And I can represent this in one of two ways. So 6.02 times 10 to the power of 23 atoms over 1 mole of Fe, or I would write this as 1 mole of Fe over 6.02 times 10 to the power of 23 atoms. Again, depends on what unit you want to cancel out. Another example, if you've got H2O. H2O is a molecular compound, which means I have 6.02 times 10 to the power of 23 molecules. Again, I can represent this as 6.02 times 10 to the power of 23 molecules over 1 mole H2O, or as 1 mole H2O over 6.02 times 10 to the power of 23 molecules. Either way, depending on the situation. And lastly, I've got NaCl, which is a ionic compound. So I would use the unit formula units. So you'll notice that we're not actually talking about particles, or we're not specifically stating particles, but we're still referencing different types of particles. So I would say atoms if there's an element that's by itself, molecule if we're referring to a molecular compound, and formula units if you're referring to an ionic compound. Okay, so let's actually put this into practice and take a look at an example problem. A sample contains 1.25 moles of nitrogen dioxide. So I'm just going to write this as its chemical formula, nitrogen dioxide. And the question is asking how many molecules are in this sample. So I'm going to start off with what I'm given in the question. So notice that this number has 3 significant digits. That'll come into play later. So part A, I'm going to write down whatever number I'm given in the question. That's always really good practice while we're using dimensional analysis, is to write down the number that you are provided in the question and recognize what unit you want to end up with. So how many molecules are in this sample? And if I take a look here, NO2 is a molecular compound, so I'm either going to have 6.02 times 10 to the power of 23 molecules over 1 mole of NO2, or the other way around. So 1 mole of NO2 divided by 6.02 times 10 to the power of 23 molecules. Now, I've got molecules, or I have to end up with molecules. So which of these two would I use? So would I use the molecules at the top and the moles at the bottom, or the moles at the top and molecules at the bottom, so that I can cancel out the unit of mole? So what I would have to do actually is to put the moles at the bottom, right? And in the conversion factor, we always know that the number 1 is written right where the moles are written, and I would have molecules at the top, right? And 6.02 times 10 to the power of 23 is the number of molecules that I have for every 1 mole. So if I type this into a calculator, the number that I will end up with is 7.525 times 10 to the power of 23. Now, remember, we mentioned at the beginning of the question that there were 3 significant digits in the question, which means there should be 3 significant digits in the answer. So I only need 3 of these numbers. So I have to round out this number. So this number is a 5 right now. So if I'm rounding this number, I would get 7.53 times 10 to the power of 23 molecules. Okay, let's look at part B. Now, part B is taking this a step further and asking how many atoms are in this sample. Now, we already solved for molecules because that's the type of particles that was in this compound. Now, if you're given a molecule and you're asked to find atoms, you have to identify a new conversion factor. So I'm going to write this over to the side. So in one molecule of NO2, how many atoms are there? All we would have to do is count, right? So there's one nitrogen and two oxygens. So in one molecule of NO2, there are 3 atoms. That's the conversion factor that I would have to use now. So I'm going to start off with how many molecules I have, which is 7.53 times 10 to the power of 23 molecules. Right? And I want to end up with atoms at the end. So I have this new conversion factor here, molecules and atoms. I would have to make sure that molecules go on the bottom and atoms go at the top. So for every one molecule, there are 3 atoms in NO2. So I have to do 7.53 times 10 to the power of 23 times 3 to find out the number of atoms. Now, something else that I will notice, or I'll note down to you, is instead of writing just this number, I would actually have to write the more accurate number possible. So when I'm typing into a calculator, I have to use the existing number, the true number that's not rounded, in doing my calculation. But writing it down, I'm going to write it with the appropriate number of sig figs. So 7.525 times 10 to the power of 23 times 3 will give you 2.2575 times 10 to the power of 24. Again, I have 3 significant figures in the question, and I need to round to 3 significant digits in my answer. So my answer is going to be 2.26 times 10 to the power of 24 atoms. Right, the reason why I had to use this conversion is because the type of compound that I have is NO2. So NO2 is a molecule. So if I was using Avogadro's number, I can only solve for the number of molecules. To find atoms is to take it a step further, which is to look at the next conversion factor, which is 1 molecule equals 3 atoms. Okay? In this situation, I'm given a value of moles, which is 0.0178 moles of iron. And they're asking us for how many atoms are in the sample. So unlike the previous question, the type of particle that I'm given in the question itself is an atom, right? This is an element that's by itself. So 6.02 times 10 to the power of 23 atoms in 1 mole of Fe, or 1 mole of Fe over 6.02 times 10 to the power of 23 atoms. Right, so these are the 2 conversion factors that I can get based on the fact that I'm given Fe in my question. So I want to cancel out the unit of moles of Fe, and I want atoms to end up as my answer. So I'm going to write atoms at the top and moles of Fe at the bottom. So for every 1 mole of Fe, there are 6.02 times 10 to the power of 23 atoms. And when I multiply this out, I'm going to get 1.07156 times 10 to the power of 22 atoms. Notice in my question, I've got 3 significant digits because zeros on the left side do not count. So the 3 significant digits that I have here, I have to represent my answer at 3 significant digits as well. So I'm going to round out 1.07 times 10 to the power of 22 atoms. And this is my final answer. Let's look at one last example in which we are given the number of formula units, so 7.71 times 10 to the power of 24 formula units. And I'm asked to find the moles of aluminum oxide. So there's formula units of aluminum oxide, which, let's just take a look. This is an ionic compound, which means that the units that we would find with Avogadro's number, or the conversion factor with 1 mole, would be formula units, right? So I can use my Avogadro's number with the formula units, and then I have to find the number of moles. So I can represent this as 1 formula unit, 6.02 times 10 to the power of 23. Sorry, for 1 mole is equal to 6.02 times 10 to the power of 23 formula units. Or I can write this as 6.02 times 10 to the power of 23 formula units over 1 mole. So I can use either one of these relationships. The reason why I cannot find atoms is because this is an ionic compound. I'm solving for formula units. The only thing that I can use Avogadro's number with is to find the number of formula units. So I have this many formula units, and I want to find the number of moles in that value. So what I would have to do is I want to cancel out formula units, so I'm going to write formula units at the bottom. And I want moles at the top. And remember, wherever there's the mole, I'm going to write the 1. And wherever there's the type of particle, I'm going to write Avogadro's number, 6.02 times 10 to the power of 23 formula units. So if I complete this calculation, I'm going to get 12.807 moles. So what I would have to do this calculation is 7.71 times 10 to the power of 24 divided by 6.02 times 10 to the power of 23. Something that I always notice that helps, depending on the type of calculator, you have to make sure that you're inputting brackets on the first number, especially because it's a number expressed in scientific notation, and on the second number. That really helps making sure that you get the correct answer, which, when rounded to the appropriate number of significant digits, which is 3, is going to be 12.8 moles. Now, if I were to ask you to find the number of total atoms in this compound, you would then have to find a conversion factor where 1 formula unit is equal to the type of the number of atoms in that compound, right? So that will be a step further in that first example that we've done. What you have to remember is when you are given a type of element or molecule in your question, that determines what the conversion factor is between Avogadro's number and 1 mole, right? So in this case, I was given an ionic compound, which is why when I'm using Avogadro's number, I have to use formula units. In this case, I was given an element in the question, which means that I can go from 1 mole to atoms. And in this case, I was given 1 mole, 1 molecule, so then I know that 1 mole is equal to Avogadro's numbers of molecules. Okay, that's pretty much it.